Hi, and welcome to a video where we introduce the topic of transfer learning. So what exactly is transfer learning and why do we need it, or why is it useful? So firstly, as I may have mentioned previously, training deep convolutional neural networks is often a very slow process. Networks like VGG in particular are very heavy with parameters. VGG has 138 million parameters, and ResNet also, while it has less parameters, has 50 hidden layers which add just complexity and training time to the network. So while these networks attain excellent performance on vast datasets like ImageNet, they're extremely performance or computational intensive to train. Sometimes you actually need an array of GPUs, that's multiple GPUs, training these networks on these huge datasets for multiple weeks on end to reach a good point of performance and convergence, okay? So that isn't possible, especially you can't train these type of networks on your CPU laptop based. Even your GPU, if you're taking advantage of your GPU in your laptop, it's not going to be quick enough at all unless you have a very high performance gaming laptop with a 1080 NVIDIA 1080 mobile GPU. Maybe that can be okay, but you're still going to need to train these things for days on end to reach a good point. So how do we get around that? Well, what if there was a way to reuse these previously trained models for your own classifiers? So as you've seen, Keras ships or includes some pre-trained image networks for weights for networks such as ResNet 50, VGG16, Inception, and MobileNet, and many others. And these weights have already been tuned to detect thousands of low-level, high-level, mid-level features in that ImageNet dataset, which contains thousands of 1,000 classes of images. So what if now we can use these features that they have learned from those images in ImageNet to train our own classifiers? Well, we actually can, and it's quite simple. So that brings us to the topic of transfer learning. Transfer learning is basically transferring knowledge from one trained network onto another. So here's a definition from the deep learning textbook that says, you can click this link on right here, it brings you to the deep learning textbook that I quoted this from, where it states transfer learning and domain adaptation refer to the situation where what has been learned in one setting is exploited to improve generalization in another setting. And that's exactly what we do with transfer learning. So in transfer learning, in applied to computer vision, we take a pre-trained deep CNN, one of these three or maybe one of the others, and use it, the already trained network, I should say, typically on ImageNet, or pretty much always on ImageNet, because Keras only ships with the ImageNet weights for these networks. And we use the convolutional layers, those trained convolutional layers, to aid our image classifying tests. So what we're doing, we're taking our already trained CNN and training it on our new data set. So we're not actually training though the previously trained network. What we're doing, we're just going to train a top layer. And I'm going to explain it to you with some diagram in the next few slides. But what I'm going to say is that what we do is that we freeze the lower layers of those pre-trained CNNs and just train the top layer or the fully connected layers only. You can even train more, depends on what layers you want to freeze and what layers you don't want to freeze. And then, actually, as I say it here, sometimes you can go back and train the lower layers if you want to improve your performance. But imagine you're taking a VGG network that's been trained extensively and you're just going to train the top layers of it with just like a minority of parameters, like maybe a couple 10,000 parameters or more, or less, depending on what layers you freeze. And it trains much more quickly on your data set as well. So you can extract some amazing performance by taking advantage of transfer learning. So this is an example of what we do. This is not a complex network. It's just illustrative purposes. What you do in transfer learning is that you freeze the weights of a pre-trained convolutional neural network here, and you just take your input data set, unfreeze, change the top layer, use the top layer of what your number of classes are, how much fully connected nodes you want as well. And you just train this new model you've kind of meshed together on your data set. And then this is exactly what I said. You train only the weights in the red here. So just to reiterate, transfer learning is where you freeze the pre-trained lower convolutional layers that are well-trained and capture universal features such as edges, blobs, curves as well, maybe even more complex patterns and stuff like that. And what we do, we replace the top FC layer of those pre-trained networks with your own, mainly because you want to be training to fit a different number of classes. So in this case, you're going from 1,000 classes to, say, a binary simple thing you want to do, like say it's a cats versus dogs type image data set you have. And we can use a small learning rate to take advantage to help distorting the newly initialized weights. You don't want to jump over the global mean. So you just want to use a small learning rate to help that, okay? So this is just a general process here. Freeze lower layers, add our own fully connected top layer, use a small learning rate size, and you're good to go. Okay. So what have we learned in this chapter, this basic chapter that introduces the topic of transfer learning? Well, you've learned the need or the importance of transfer learning. We've learned how it works, how we freeze the lower layers and just train the top layers, and which is generally the step-by-step guide of doing it. So now let's move on to the next video where we actually implement transfer learning using Keras, TensorFlow, and in Python on the Sapphire 10 dataset. So stay tuned.